Hi there, this is video 2C2 part 2. We are going to talk about characteristics of a logarithmic function and specifically discuss the key characteristics: domain, range, concavity, rate of change, and end behavior. So, what I want to go ahead and do is focus in on a logarithmic graph. So here is in general what a logarithmic function looks like, log base b of x. Now we can have some transformations to this. I can have an a value in front. This is where a is greater than 0, because obviously if it is negative, then we get a horizontal reflection, and it would look like this example here. Okay, and specifically too, this is when the base is greater than 1. Or it's rare, but it is possible that you have a base that is between 0 and 1. So you get the inverse of exponential decay, which would look like this function here. Kind of almost looks like the reflection of the base b with a negative a value. And then obviously if we reflect that, then it looks like a normal logarithm. Okay, so what I do want to point out here is that this logarithmic function by nature is increasing. It has a positive average rate of change. And when a function is increasing, the average rate of change is positive, and we can see this here. Furthermore, about this function being increasing is that the rates of change, if you go ahead and envision, sorry, my pen's lagging on me. There we go. Oh, maybe it just doesn't like that part of the document. Okay, there we go. You can see how the average rate of change is decreasing, right? This slope would be much greater than this slope here. This is flatter. So the average rate of change here is decreasing, which means that this graph is concave down. Okay, so very important to understand this, that when your rate of change is decreasing, a graph or a function is concave down. Okay, now let's go ahead and look at the reflection of this. So here is a graph, and this average rate of change from here to here is negative. So obviously, sorry, I wanted to do it on this graph here. So from here to here, this is a decreasing function. So when the average rate of change is negative, your function is decreasing. But let's go ahead and look at the average rate of change. This is a negative average rate of change, as we just said, so it's decreasing. But look at the next average rate of change. So if I go from here to here, do you see how it is less negative, and it's almost approaching 0? So here my rate of change is increasing. It's negative. Here it's less negative, and over here it would be even less negative. So that's an increasing average rate of change, which means that when rate of change is increasing, you get a concave up graph. And you can kind of see that, right? This graph is concave up. It's opening upwards. Here, average rate of change is decreasing. This is concave down. Okay, so important facts there. End behavior. We talked about end behavior in the previous lesson. End behavior for logarithmic functions. We have a vertical asymptote for our function, x equals 0. So as we approach 0 on that side, the end behavior is going to be unbounded. It will go to negative infinity for normal logarithmic functions, or positive infinity if you have a reflection. Okay, and then the other side, you're going to have an unbounded function. So as x goes to positive infinity, you'll either go up to positive infinity or down based upon kind of what's going on. Okay, all right. So logarithmic functions, they're always increasing, always decreasing, and or always concave up or always concave down. So it's always one or the other. They do not have any extrema, maximums, minimums, except if it is a restricted domain, if we kind of cut off ends of the logarithmic function. And there's no points of inflection. Like I said, it's always one concavity. We never change between, okay? So let's go ahead and look at some AP questions that are going to be asked. Here's example number 1. They give a function d given by d of x equals -2 log base 3 of x. Which of the following is true about the graph of d? And how my brain always processes these is I like to envision, okay, what would a normal logarithm look like? Log base 3 of x. Well, that would look like this, something like this, increasing concave down. Okay, but what are we doing to this graph? Oh, we're multiplying by -2. What does that do to my graph? So we get a stretch and we get a reflection. So maybe something like this. This would be our negative and a vertical dilation by a factor of 2. So what is this graph? Well, this graph, it looks like it's concave up. Okay, so I can cross out C and I can cross out D. And they say, be very careful here. Ooh, those tricksters. They say the rate of change is decreasing or the rate of change is increasing. So this is still tied to concavity. Well, if you're concave down, by definition, your rate of change is decreasing. So our answer here, oh sorry, we crossed off C and D. We are concave up, and so rate of change is going to be increasing. The answer here is B. We're concave up, not concave down, and so the rate of change is by definition increasing. Okay. Similar question here. Please go ahead, pause video, try this example. Okay, hopefully you pause this one. Here we have log base 4 with a factor of 3. So again, this logarithmic function just looks like this. This is an increasing function, and it is increasing at a decreasing rate because it is concave down. So this is increasing, and it is concave down. So again, what does this mean for rate of change? Because sometimes they define these in terms of rate of change. Your rate of change is positive, and here your rate of change is decreasing. So it's increasing at a decreasing rate. And so I believe our answer here is going to be A. Okay? All right. Next. Practice 1. Go ahead, pause the video, try this example. Okay, so this one kind of had a curveball. We had the base that is between 0 and 1, so note that this is the inverse of exponential decay. So you kind of start with the reflection of a logarithmic base. So it looks like this. This is decreasing concave up. So if I reflect that, I have a negative A value here. It's going to be increasing concave down, increasing concave down. So we're definitely looking at C or D. And they again say P is increasing and the rate of change is, well, if we're concave down, rate of change is decreasing. So answer was C. Did you get it? Hopefully you did. Okay. Couple more questions here. Let's go ahead and talk about end behavior. The function w is given by w of x equals -6 natural log of x. Which of the following describes the behavior of the graph of w as x increases without bound? So again, just by the definition here of what they're giving us, x is increasing without bound. That's going to be C or D. I can throw away A and B. And then I need to know, okay, first of all, forget the -6. What does natural log of x look like? Y equals ln x. That is going to look like this. And so if I multiply by a negative and a -6, I'll get the reflection and a stretch. So something like this. So it looks like as x goes to positive infinity, that is these values. As I go this direction, where are my y values going in? It looks like they're going to negative infinity. So our answer here is C. Pretty straightforward here, okay? All right, practice problem here. We've kind of already talked about this in the previous example. The function z is given. Which of the following best describes the behavior of the graph of z as the value of x becomes arbitrarily close to 0? Pause video, I'll show you the answer here in a second. Okay, hopefully on this one, just again by the words, x becomes arbitrarily close to 0. Hopefully you threw out C and D, and we're looking at these limit statements here as x becomes close to 0 from the right side. And then your graph is just a normal logarithmic function. I have a 1/2 factor, but that just kind of compresses it. Doesn't change the end behavior. So as we get closer and closer to 0, it looks like my y values are going to negative infinity. Correct answer here would be B. Okay, last topic. I already talked about logarithmic functions. They're strictly increasing and decreasing. They do not have extrema unless I go ahead and I restrict the domain as this question is doing. They're saying, hey, here's a function f, log base 2. If your domain is restricted from 1 to 32, which of the following is true of f? And they give me some minimum and maximum values. So what I'm going to do is I'm just going to take, because it is a strictly increasing or decreasing function, I'm going to take these values and I'm going to evaluate log base 2, and I'm going to take that first domain value, 1. Well, that gives me 0. And I'm going to take 32, log base 2 of 32, and this is going to give me 5. Okay, so just note that it's these values, and then here, okay, what I also notice is that my domain is less than 32, so I'm actually going to be really close to 5. So I feel like this is a trick question. I would look for a minimum of 0, maximum of 5. I really like A, but the missing underline there gives me some pause. So I really wish that was underlined, then I feel really comfortable with A, but I feel like the answer here is going to be B. Let me check my notes. Yep, I got it right. No maximum because it's not equal to 32. So you're going to get infinitesimally close to 5, so I guess they're rendering that here as no maximum. But again, this would just be a graph that is kind of chopped off on the ends. So keep that in mind when you try this practice problem here. Given the function log base 3 of x for 3 less than x, less than or equal to 81, which of the following is true of g? Is the minimum 1, maximum 4, or a mixture of those? Go ahead, pause. I'll show you the answer here. Okay, so again, if you just evaluate g at your ends, 3 and 81, you get 0 and 4. But again, because it's not equal to 3, we're going to say no minimum. I know it's kind of weird. I don't really like this question. Or sorry, that should be our answer. No minimum and a maximum of 4. Okay, kind of a weird notation there. Anyway, that is logarithmic functions. You got a graph that curves, okay, like this guy, increasing, concave down, and yeah, that's it. Okay, hopefully you learned some of the key features of a logarithmic function. See you next time.